Hello and welcome to lab number 19 in our light and optics series of experiments. The title of this lab is Interference and Diffraction through a Pinhole. By a pinhole, we consider a small circular aperture whose size is on an order of scale of a wavelength of light, and it turns out that when a light passes through such a small aperture, it is going to diffract, creating a very distinct diffraction pattern on the back screen that consists of a central disk, so-called airy disk, and a whole bunch of concentric bright annular rings around that center spot. So in this lab we are continuing our exploration of diffraction as a phenomenon. It's important to mention that there's two different types of diffraction. If we are observing diffraction in an immediate neighborhood of a diffracting objects, we are talking about so-called Fresnel diffraction, and then if we are at a far distance away from the diffraction object, we are talking about so-called far field or Fraunhofer type of a diffraction. It's important to mention that diffraction has found many applications in the real world and the real science. Very often it's being used to measure dimensions of small features. In certain instances, diffraction is actually limiting the performance of a specific optical system, and in such a case we are talking about so-called diffraction-limited imaging processes. So in this lab we are focusing our attention to diffraction of light. We are going to explain the diffraction of light as it's passing through a pinhole, and then we are going to set an experiment in which we are going to observe diffraction pattern that's been created by the laser light passing through a diffraction pinhole, and finally to conduct a few measurements and calculations to figure out the size of airy disk in the diffraction pattern created through the pinhole. The equipment to be used in this lab consists of red laser diode module, a laser holder, a circular aperture or a pinhole of a size of 0.1 millimeter. We will use the lens holder to hold the circular aperture, and then for the measurement we will use a measuring tape, a protractor, a pencil, and finally a large white sheet of paper. Here's the setup for this lab. As you can see, we have mounted our red laser diode module onto the laser holder, taped it down. And then here in front of the laser module we have positioned our pinhole index card with the size of 0.1 millimeter, and you have to establish a proper alignment so that the laser beam is shooting through the pinhole aperture of the size 0.1 millimeter. And that index card with a pinhole aperture has been positioned at 0 centimeter on our tape ruler that's been taped down all the way. And as you can see all the way in the back, we have the back screen. After we dim the light in the room to create for more of a dark environment, we would look at the back screen, and you can see a very distinct pattern here. This pattern is circular in shape, so we have this center disk or so-called airy disk, and then that airy disk is surrounded by the whole bunch of annular rings that create this very distinct diffraction pattern created through the pinhole. As part of this lab, you would want to use your pencil and mark this center airy disk, and then do proper measurements of its diameter, and then do the proper calculations. In addition to making the sketch of the airy disk on the back screen, you would also want to measure the distance from the pinhole aperture all the way to the back screen. So as we already indicated, we have positioned our pinhole index card at the position 0 along our tape ruler, and then over on the other side we can see that the back screen is positioned at about 120 centimeters. So that's going to be our distance from the pinhole all the way to the back screen. So distance equal to 120 centimeters. Okay, so here's our improved sketch of the diffraction pattern we achieved using an index card with a pinhole. These are the marks that I made on a paper while being on a back screen, and then using these dots, these markings, I constructed the airy disk as well as the first bright annular ring. First we are going to measure the diameter of the airy disk both in the horizontal and the vertical direction. So in horizontal direction I'm measuring about 19 millimeters. And then in vertical direction, we are measuring about 18 millimeters. So D2 is 18 millimeters. So the average diameter of the airy disc is equal to D1 plus D2 over 2. So if we average 18 and 19, we're gonna get 18.5 millimeters. Or the average radius from here is going to be equal to the half of the average diameter, which is going to be equal to 9.25 millimeters. Okay, so the formula to calculate the radius of the airy disc is as follows. Rp is equal to 1.22 times lambda times L over D, where lambda represents the wavelength of the light that's been used in the experiment. In our case, we are dealing with a red laser diode module, so the wavelength is equal to 650 nanometers. And then L is the distance from our pinhole all the way to the back screen. And then finally, D represents the diameter of the pinhole. So in our case, lambda is going to be equal to 650 nanometers, as already mentioned, for the red laser diode module. For L, we have a distance of 120 centimeters as measured in the experiment. And then finally, diameter of the pinhole is equal to 0.1 millimeter. Okay, so let's now substitute for these values into our formula. So we have the following. (1.22) times lambda being 650 nanometers, which is equal to 650 times 10 to the negative 9 meters. So we are going to convert everything into the base units here. L is 120 centimeters, which is equal to 1.2 meters. And finally, D is 0.1 millimeter, or 0.1 times 10 to the negative 3 meters. So let's do this calculation. So we have 1.22 times 650 times 1.2 over 0.1 gives us 9,516 times 10 to the negative 3 over 10 to the negative 9 over 10 to the negative 3 is 10 to the negative 6 meters, which can be converted into 9.516 times 10 to the negative 3 meters, or equal to 9.516 millimeters. So this is the calculated value for the diameter of the airy disc, for the radius of the airy disc. And in the previous step, we measured the radius of the airy disc, came up with a value of 9.25. So we can compare the two values, the nominal or calculated one and the one that we measured, and calculate the percentage error. So in our case, the percentage error is going to be equal to the absolute value of R measured minus R calculated over R calculated times 100. So if we substitute for the values, we have the absolute value of the measured, which is 9.25, minus the calculated value of 9.516 over 9.516 times 100, which would give us the following: 9.25 minus 9.516 is minus 0.266. Absolute value is going to be without the negative signs, divided by 9.516 times 100 gives us the percentage error of 2.795%, which is really good for this type of experiment.